Welcome. This is going to be part 2 of our advanced topics midterm review. We're resuming with question number 4. So let's get right into it. Notice we have, in this question, it's in 2 parts, frequency, wavelength, and energy. Well, if you remember, we have a couple of formulas that we use. Let's define a few things. You need to know that wavelength is this symbol lambda. Frequency, well, you can either use one of two, F. Your teacher might have given you this V-shaped. Both of these represent frequency. Energy, of course, is a capital E. Now, once you know those, you know that if you have a formula that, well, you're given frequency, you have to solve wavelength. When you look at your formulas, you're going to see there's only one formula that can possibly be used to answer such a question. It's this one, speed of light equals wavelength times the frequency. You're given the speed of light. Now, I'm going to apply this one here, 3.00 times 10 to the 8th meters per second. Wavelength is what we're solving for. I'll leave it as a lambda. The frequency we're told is 6.0 times 10 to the 17th cycles per second. That's also the same 1 per second. You're not responsible for units. And when we calculate this, we divide both sides by this 6.0 times 10 to the 17th cycles per second. And we get an answer of 5.0 times 10 to the negative 10 meters. All right. In the second part, well, I hope you didn't forget to look up at the first sentence. We need the frequency again. There's the energy formula. Energy is the product of something called Planck's constant times the frequency. Well, Planck's constant is given to you. It's 6.63 times 10 to the negative 34 joule seconds. We multiply that by the same frequency of 6.0 times 10 to the 17 cycles per second. Notice how the seconds cancel out, leaving us with joules. And we have a final answer of, bang, 4.0 times 10 to the negative 16 joules, which is a fairly energetic photon. Number 5. Lattice energy can be defined as the amount of energy required to completely separate 1 mole of a solid ionic compound into its gaseous ions. How do I determine the relative amounts of energy required to perform this following task? Well, the first thing that we look at is we look at the relative charge magnitudes, or the relative, or the relative charge quantities. In other words, the compound that contains the ions with the greatest positive and negative charges must have the greatest lattice energy. So the first thing you always should do is assign charges. Notice K is +1, Cl is -1, Ca +2, Cl -1. Doesn't matter if there are 2 of them. Well, that gives it away right here. Greater magnitude of charges, charge quantities, the greater the lattice energy. Second one, do the same thing. Assign charges. Calcium ion +2, -2, strontium +2, oxygen -2. We have a tie. We can't use the relative charge quantities, so our tiebreaker is always, we're going to use the relative sizes of the ions. And whichever compound has ions that are smaller, is going to have the greater lattice energy. Now, if you notice, we're going to compare calcium and strontium. Those are the only different ions. And it turns out they're both in group 2. If you remember, as we go up a group, the ions in the atoms get smaller. Well, that means that calcium is a smaller ion than strontium is. And that has an inverse relationship. The smaller the ion is, the greater the lattice energy. It turns out that if 2 ions are smaller, they're closer together and have stronger attraction, and therefore need even more energy to be pulled apart. C, assign charges, +2, -1, cesium +1, bromine -1, that's easy. We choose the greater charge quantities. So that has to be more greater lattice energy. D, Na plus 1, N minus 3, Na plus 1, F minus 1. Oh, no contest again. These have the greater charges, the greater charge quantities. This is a -3, which is a very negative charge. Number 6, draw the electron dot diagram for BF3. One thing I want to tell you not to do, sometimes it's tempting to draw valence electrons and then connect the dots. That works if we're operating by the rule of 8. However, sometimes the central atom has what is called a reduced octet or a expanded octet, meaning fewer than 8, greater than 8. So the best approach here is always to use the following approach. To count up the total number of valence electrons that must be in the molecule, boron has 3 valence electrons. We have 3 fluorines, so that means 3 times 7 in each of the fluorines. So when all is said and done, I have to have 24 valence electrons in my drawing. You draw the central atom. You surround it with the peripheral atoms. I'm positioning them correctly because I know how it looks. If you, let's say you did this, you're not going to, it's a little scrunched, but you can still do it that way. It turns out it looks more like this. But remember, you're only drawing the atom to count up what we call bonding pairs, bonding domains, and non-bonding domains. So I'll come back to that in a moment. Notice I have drawn single bonds. They're probably going to stay as single bonds. I need to give the outer atoms their full octet, unless, of course, you're hydrogen and you only have 2. And if you notice, I've drawn 8 plus 8 plus 8. That's what I need. So I am done. All right, at this point, I'm going to count up the number of bonding and non-bonding domains in the central atom. Well, a bonding domain is a single, double, or triple bond. Well, I have 1, 2, 3 singles, so I have 3 bonding domains. What would a non-bonding domain look like? Well, if we took water, for example, on the central atom, you have 2 pairs of non-bonding domains, and you have 2 bonding domains. BF3, the boron, has no non-bonding domains. Well, what does it mean to have 3 bonding domains and no non-bonding domains? Well, I look below. You get credit for drawing your molecule. Again, boron looked like this. It had 3 bonding, no non-bonding domains. So you need to identify that as being trigonal planar. That's the shape. It's flat, and it's arrayed. The fluorines are arranged in triangular fashion. Okay. Number 7 is a calorimetry question. It's the one that no one's really that crazy about. What are we dealing with here? I have a certain mass of water at a temperature of 30. And I'm going to mix that with some much warmer water. I know how much there is, 800 grams, and I know that warmer water is at 95. I know that when all is said and done, once they're mixed, you're going to have a final temperature of 45. I want to know what the mass of the cold water is. Well, a little drawing might help you visualize this. Bang! So this is what I was saying. I have this mass of water. I don't know how much I have. I know its specific heat is 4.18 joules per gram. It's water, after all. Its initial temperature is 30. That's why I'm drawing this with the cooler blue color. I'm putting it into here, which has 800 grams of this hot water. Again, same specific heat capacity. And when all is said and done, the temperature of both samples of water have changed to 45. If you notice that the hot water, in becoming 45 degrees, has decreased in temperature by 50 degrees Celsius. You'll also notice that the cooler water, by contrast, in becoming the 45-degree water, gains 15 degrees Celsius. So, what does this look like in terms of a formula? Well, first of all, remember that it's the hot water. We're representing with Q, with the negative sign showing a loss of energy. All that energy lost by the hot water has to be gained by the cold water. Since both are changing their temperature, we're going to use the MCAT formulas for each one. MC delta T equals MC delta T. Notice I have 800 grams of the hot water, and I want to solve for the amount of cold water. Notice they're both water, so they both have the same specific heat capacity. The hot water, notice, is losing 50 degrees Celsius. That's why that's minus 50. The cold water, on the other hand, is gaining 15 degrees Celsius. So when we do our math, so the product is 167,200. Notice the negative times a negative became positive, so that disappears. I divide both sides by 67.2, and I get an answer of 2,670 grams. That's a lot of water. Number 8 deals with hybridization. This is for NH3 and SF4. What does hybridization mean? It means that you're taking 2 or more different pure sublevels, orbitals I should say, and you're creating a hybrid orbital. That's all you need to know about that. It turns out that if you have what we call 2 effective pairs on your central atom, you have something called sp hybridization, meaning I took S and a P, one S and a P, and I made a hybridized orbital. If I have 3 effective pairs, and I'll explain what that is in a moment, it means that I took sp and p, and I made something called sp2. If I have 4 effective pairs, I took sp, p, and p, and made something called sp3. Now I've run out of s's and p's, so now if I want more, I have to go dig down deep into the D sublevel. So I took an S, a P, a P, a P, and a D. That's 5 effective pairs, and that means DSP3. And finally, if I want 6 effective pairs, I need an S, a P, a P, a P, a D, and another P. Let me do that again. S, P, 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 a D, and a D, and that gives me a total of 6 effective pairs, which we formally write as D2SP3. Now, due to time, I can't show you how I came up with these molecules, but this is what the molecule for NH3 looks like. Now, an effective pair can be one of a couple of things. An effective pair can be either what we call a non-bonding domain. It also could be a single bond, a double bond, or a triple bond. So if we look at NH3, if you notice, I have one non-bonding domain, and I have a single bond, a single bond, a single bond. That means a total of 4 effective pairs, which means that NH3 is sp3 hybridized. SF4, by contrast, has one non-bonding domain. It has a single, a single, a single, a single. That's a total of 5 effective pairs, so that means it is what we call dsp3 hybridized. Number 9. We give you a Lewis dot structure of something called the sulfate ion, and we want you to calculate something called the formal charge of the sulfur and one of the oxygen atoms. We do this to evaluate the likelihood that the drawing that we have drawn, the molecule that we've drawn, exists in that arrangement in nature. Hello. Oh, Assistant Principal walked up. So we're not going to do that here. We're not going to put the charge to the test. But we're going to calculate formal charge. I think I have just enough time to do that. First of all, you need to know the formula for formal charge. The formal charge equals the number of valence electrons minus the number of non-bonding electrons on that given atom minus the number of bonds. Let's apply that to sulfur. Sulfur is 286. It has 6 valence electrons. How many non-bonding electrons are on it? None whatsoever. How many bonds? 1, 2, 3, 4. 4. 6 minus 4 is a positive 2. Oxygen, by contrast, is 2, 6. Oh, just coincidentally, it also has 6 valence electrons. Notice here, I have 1, 2, 3, 4, 5, 6 non-bonding electrons, and I just have 1 bond. So 6 minus 6 is 0, minus 1 is negative 1. So those are the formal charges of those atoms. Well, I have to go on to a part 3. I'm just about to run out of time. See you again on YouTube.